CPU instruction set. Learning objectives. At the end of this topic, you will be able to recognize machine instructions in an instruction set, identify the elements in machine instructions and their importance, know the different types of operands that are expected in an instruction, reason the existence of a large number of instructions in a machine's instruction set, learn the usage of machine codes to write simple programs. Outcomes. By the end of this topic, you will be able to apply the different modes of addressing the contents of a RAM to improve the performance of a computer system, implement different computer instruction sets. A general-purpose computer CPU consists of a control unit which is defined to generate a unique set of control signals for every instruction in the instruction set. It also has a set of registers to store data and instructions, and has ALU to execute arithmetic and logical instructions. Instruction set is the software component of a computer system. Usually, a computer programmer writes codes in high-level language like Pascal or C. But what connects him to the machine is the instruction set. Instruction set consists of machine instructions which are in binary language like the one shown. 00001010, which is load MQ, and which means to transfer contents of register MQ to the accumulator AC, a register. These instructions are binary codes which are realized in hardware, and the control unit is programmed or hardwired to generate the corresponding signals for these realizations in the hardware to respond and act. Each instruction contains all the information required by the processor for execution. The instruction shows what operation is to be performed, what type of instruction it is. Depending upon the type of instruction, how much data are required to be operated, from where the data or result is to be moved or shifted, and to where to jump while in the instruction cycle in order to execute another program as subprogram or interrupt handler program. Computer designer comes up with a general instruction format for accommodating all these issues. The format of an instruction is usually depicted in a rectangular box, symbolizing the bits of the instruction as they appear in memory words or in a control register, and the bits are divided into groups called fields or elements. A simple instruction format is shown. The most common fields found in instruction formats are an operation code field that specifies the operation to be performed called opcode, an address field that designates a memory address or a processor register, and the mode field that specifies the way the operand or the effective address is determined. Let us take the field opcode, which tells the CPU to perform an operation. Operations or instructions can be of four types: data processing, which are for arithmetic and logic operations; data storage, for moving the data into or out of registers and memory locations; data movement or I/O instructions; and control instructions that instruct the CPU to test and branch or jump. The operations must be executed on some data called operands stored in computer registers or memory words. The data within registers can be called by their names, and the data within memory can be called by specifying the address of location within the instruction. This is direct addressing, where the operand comes from the address specified. For example, the address of the operand in this instruction is 457. And the operand is found at 457. Sometimes the operand is located in a place whose address, called the effective address, is stored in another location, and that location is specified in the instruction. This is called indirect addressing. In this case, the address of the operand is 300, and the content of 300 is 1350, which could have been operand, but it is not. Instead, it is the effective address of the operand. Apart from indirect and direct mode of addressing, there are other methods which will be dealt with under addressing mode. Let us consider a simple basic computer of accumulator type organization where all operations are performed in an implied accumulator AC shown in this organization. See a memory of size 4096 words of 16 bits each. Instruction register IR is of 16 bits. Similarly, data register DR, temporary register TR, and accumulator are 16 bits each. Address register AR stores the address and memory of 4096 is 2 to the power of 12 words, so AR is of 12 bits. Similarly, PC, which stores address, so is 12-bit size. The instruction formats were the types of instructions categorized on the basis of references for operands is shown here. I is equal to 0 or 1, and opcode bits 000 to 110 are for memory reference instructions. I is equal to 0 is for direct and I is equal to 1 for indirect. The resulting instruction set is shown here. Memory reference, register reference, and I/O instructions. Try interpreting the instruction 0000 110101 101001. First, we break the 16-bit instruction into 3 parts. This shows I is equal to 0, which means the addressing mode is direct. From the format for memory reference instructions, the next 12 bits correspond to an address in memory, which in hex is D69, and 3433 in decimal. The instruction means and the content of memory location 3433 with the content of accumulator. Similarly, 011110 0001 000000 interpreted as register reference instruction 7080 in hex, which means circular right shift AC and E. E is a carry flag. Machine instructions operate on data which might be one of these: addresses, numbers, characters, and logical data. Addresses can be considered as data when effective addresses of operands are sought. Calculations must be performed on the operand reference in an instruction to determine the main or virtual memory address. Numbers are another type of operand. It can be a binary integer, binary floating point, or packed decimal number involved in calculations. The third type of data is characters. These are text and character strings represented in some character codes like International Reference Alphabet (IRA) or American Standard Code for Information Interchange (ASCII). Logical data. An n-bit consists of n 1-bit items of data, each item having a value of 0 or 1. When a data unit is viewed in this way, when they are considered as logical data, the number of different opcodes varies widely from machine to machine, but a typical categorization of all the instructions can be done in the following way. A few instructions of the basic computer instruction set can be recognized as one of these types. INP, OUT are data movement or I/O instructions. STA, LDA are data storage. AND, ADD, CLA, CLE, CMA, CME, CIR, CIL are data processing instructions, and BUN, BSA are control instructions. Similarly, another example could be IAS Computers instruction set. Here we come to addressing modes. Their immediate mode, direct mode, indirect mode, register mode, register indirect mode, displacement mode. Let us say A represents the contents of an address field in the instruction. R, the contents of an address field in the instruction that refers to a register. EA, the actual or effective address of the location containing the referenced operand. And X within square brackets represents the contents of memory location X or register X. The simplest form of addressing is immediate addressing, in which the operand value is present in the instruction, that is, operand is equal to A. Another simple form of addressing is direct addressing, in which the address field contains the effective address of the operand. EA is equal to A. With direct addressing, the length of the address field is limited in address range. One way to have the address field refer to the address of a word in memory, which in turn contains a full-length address of the operand. This is known as indirect addressing. EA is equal to A within square brackets. Register addressing is similar to direct addressing, but in this case, the address field refers to a register rather than a main memory address. Here, EA is equal to R, where R is the name of a register. Register indirect addressing. This mode is analogous to indirect addressing. Here, EA is equal to R within square brackets, which means R is a register in the CPU whose content is the address of operand in memory. Next is displacement addressing. This method combines the capabilities of direct addressing and register indirect addressing. The effective address is obtained by the following computation. Effective address is equal to the sum of address part of instruction and the content of CPU register. That is, EA is equal to A plus R within square brackets. This way, there are three addressing schemes: relative addressing, base register addressing, and indexed addressing. In relative addressing, R is PC, that is, program counter's content is added to A to get the effective address EA. The received address is relative to the address in PC. Base register addressing. In this mode, the content of a base register is added to the address part of the instruction to obtain the effective address. Next, displacement addressing is indexed addressing mode. In this mode, the content of an index register is added to the address part of the instruction to obtain effective address. An address field in an instruction contains decimal value 14. Where is the corresponding operand located for A, immediate addressing, B, direct? Consider a instruction format. We have already seen the format for a basic single accumulator organization computer. The types of instructions were based on references to processor registers or memory or input-output. The format varies in length and content according to the organization and complexities involved in addressing. For example, the formats for PDP-11 are shown here, which is different 16-bit, 32-bit, and 48-bit formats. There are three types of CPU organizations: single accumulator organization, general register organization, and stack organization. In accumulator organization, all operations are performed with an implied accumulator register. The instruction format in this type of computer uses one address field. For example, add X, where X is the address of the operand. The instruction format in the general register organization computer needs three register address fields. For example, add R1, R2, R3 to denote the operation. Add the contents of the registers R2 and R3 and store in R1. Computers with stack organization have push and pop instructions which require an address field. The instruction add in a stack computer consists of an operation code only with no address field. Look at this example. X and Y are pushed into the stack using the first two instructions. The third instruction add adds the last two operands from the top of the stack. Most computers fall into one of the three types of organizations that have just been described. Variations in length of the instruction format are also expected to be implemented in different situations. Like to evaluate the arithmetic statement x is equal to a plus b into c plus d. 0 address or 1 address or 2 address or 3 address instructions can be designed. What is an assembly language and how is it helping us? We are going to see that now. A processor understands and executes only machine instructions, which we know are in binary language. According to von Neumann, the binary codes are stored in memory and are fetched one by one and are executed. If a programmer wished to program directly in machine language, then it would be necessary to enter the program as binary data. Is it possible in all situations? To answer that question, let us convert a high-level language statement into machine language. Consider the statement n is equal to I plus j plus k, which is written in BASIC. Suppose we wish to program this statement in machine language and to initialize I to 2, j to 3, and k to 4. We can do that in the following steps, say in the single accumulator organization. Consider the following memory setup for I, j, and k. The program consists of 4 instructions. Load the contents of location 201 into the AC. Add the contents of location 202 to the AC. Add the contents of location 203 to the AC. Store the contents of the AC in location 204. For more improvement, we can make use of the symbolic name or mnemonic of each instruction. This results in the symbolic program. To store arbitrary data in a location, we invent a pseudo instruction with a symbol DAT. This is merely an indication that the third field on the line contains a hexadecimal number to be stored in the location specified in the first field. For this type of input, we need a slightly more complex program. A much better system and one commonly used is to use symbolic addresses. This is illustrated in the figure. Summary. Let's summarize the topic. Instruction set is the software component which is realized in the hardware. Every hardware corresponding to the instruction is activated through control signals by control unit. Calculations must be performed on the operand reference in an instruction to determine the main or virtual memory address. The operand is viewed as numbers, which may be a binary integer, binary floating point, or packed decimal number involved in calculations. Assembly language is an intermediate language between high-level and low-level language. CPU process structure and functions. Learning objectives. At the end of this topic, you will be able to conceptualize the working of processor in detail involving instruction cycle. Understand the importance of CPU registers, which are employed for different purposes. Visualize the concept of pipelining for better CPU performance. Outcomes. By the end of this topic, you will be able to analyze performance, instruction throughput, and pipelined implementations of a simple instruction set. Apply the concept of pipelining in improving the speed of system performance. We already know from Unit 1 that CPU consists of control unit, arithmetic logic unit, and general purpose registers, and that it does the following in cycles: fetch instruction, interpret or decode instruction, fetch data, and execute instruction. To do these, the CPU has to 1. Store some data temporarily. 2. Remember the location of the last instruction in order to fetch the next instruction. 3. Store some instructions and data temporarily while executing another instruction. This means the CPU needs a small internal memory to store all these information. Internal memory's role is played by the registers in CPU. Execution of arithmetic and logic operations is done by AL unit. The control unit controls the movement of data and instructions into and out of the processor and controls the operation of the ALU. We see the internal CPU bus connecting the three components. This element is required to transfer data between the various registers and the ALU, because the ALU operates only on data in the internal processor memory. This picture shows the internal structure of the CPU. The registers in the processor perform two roles. User visible registers enable the machine or assembly language programmer to minimize main memory references by optimizing use of registers. Control and status registers, used by the control unit to control the operation of the processor and by privileged operating system programs to control the execution of programs. A user visible register is one that may be referenced by means of the machine language that the processor executes. We can characterize these in the following categories. General purpose. Data, address, condition, codes. General purpose registers can be assigned to a variety of functions by the programmer. Sometimes their use within the instruction set is orthogonal to the operation. That is, any general purpose register can obtain the operand for any opcode. This provides true general purpose register use. Often, however, there are restrictions. For example, there may be dedicated registers for floating point and stack operations. In some cases, general purpose registers can be used for addressing functions. Example, register indirect displacement. In other cases, there is a partial or clean separation between data registers and address registers. Data registers may be used only to hold data and cannot be employed in the calculation of an operand address. Address registers may themselves be somewhat general purpose, or they may be devoted to a particular addressing mode. Examples include the following. Segment pointers. In a machine with segmented addressing, see section 8.3, a segment register holds the address of the base of the segment. There may be multiple registers. For example, one for the operating system, one for the current process. Index registers. These are used for indexed addressing and may be auto-indexed. Stack pointer. If there is user-visible stack addressing, then typically there is a dedicated register that points to the top of the stack. This allows implicit addressing, that is, push, pop, and other stack instructions need to contain an explicit stack operand. A final category of registers, which is at least partially visible to the user, holds condition codes, also referred to as flags. Condition codes are bits set by the processor hardware as a result of operations. For example, an arithmetic operation may produce a positive, negative, zero, or overflow result. In addition to the result itself being stored in a register or memory, a condition code is also set. The code may subsequently be tested as part of a conditional branch operation. Control and status registers. There are a variety of processor registers that are employed to control the operation of the processor. Most of these, on most machines, are not visible to the user. Some of them may be visible to machine instructions executed in a control or operating system mode. 4 registers are essential to instruction execution. Program counter, PC. contains the address of an instruction to be fetched. Instruction register IR contains the instruction most recently fetched. Memory address register MAR contains the address of a location in memory. Memory buffer register MBR contains a word of data to be written to memory or the word most recently read. Now that we know the internal organization of a processor and the uses of its components, we can now have a closer look at what exactly happens in the instruction cycle and how the CPU does it. A more elaborate instruction cycle is shown here. So, first is the fetch phase. In this phase, an instruction is copied from the memory into one of the registers, internal memory of the CPU. What we require here are the following. Where is the instruction located? How does the CPU know where the instruction is? How is the instruction going to come into the bus? Who points to the instruction location containing instruction? Where is the instruction received in the CPU memory? How does the corresponding register know that it is entitled to receive the instruction? Let us answer these questions one after the other in order to understand the whole process of fetching instruction. 1. The instruction is at some location in the memory. 2. From a register called the program counter PC. 3. Through the relevant control signals to the memory. 4. The memory address register MAR. 5. In the instruction register IR. 6. By the control signals to the register. So in this phase, the PC contains the address of the next instruction to be fetched. This address is moved to the MAR and placed on the address bus. The control unit requests a memory read and the result is placed on the data bus and copied into the MBR and then moved to the IR. Meanwhile, the PC is incremented by 1 preparatory for the next fetch. Once the fetch cycle is over, the control unit examines the contents of the IR called the decode phase to determine if it contains an operand specifier using indirect addressing. If so, an indirect cycle is performed. The rightmost n bits of the MBR, which contain the address reference, are transferred to the MAR. Then, the control unit requests a memory read to get the desired address of the operand into the MBR. The execute cycle takes many forms. The form depends on which of the various machine instructions is in the IR. This cycle may involve transferring data among registers, read or write from memory or I/O, and/or the invocation of the ALU. Like the fetch and indirect cycles, the interrupt cycle is simple and predictable. The current contents of the PC must be saved so that the processor can resume normal activity after the interrupt. Thus, the contents of the PC are transferred to the MBR to be written into memory. The special memory location reserved for this purpose is loaded into the MAR from the control unit. It might, for example, be a stack pointer. The PC is loaded with the address of the interrupt routine. As a result, the next instruction cycle will begin by fetching the appropriate instruction. Consider a non-pipelined system which contains 5-step process. Instruction 1 is fed into the system. Time taken by instruction 1 to complete the process is 50 units. Now, instruction 2 enters the system and it takes another 50 units to complete the process. Now consider a pipelined system with 5 segments or stages. Instruction 1 enters the system. When instruction 1 enters the second stage, instruction 2 enters the system. In the same way, instruction 3 enters the system when instruction 2 is in the second stage while instruction 1 is in the third. This process is continued. The first instruction comes out of the pipeline after 50 time units. Instruction 2 after 60 time units, instruction 3 after 70 time units, and so on. Now, if we compare the time required to execute instructions in both these cases, we find a huge reduction in the time required to execute instructions in pipelined system. By pipelining, there is speed up in the process. Summary. Let's summarize the topic. Use of visible registers. Enable the machine or assembly language programmer to minimize main memory references by optimizing the use of registers. Control and status registers, used by the control unit